is 4.2, exponential functions. When we're talking about exponential functions, we have a parent function that all the other functions are based off of. Our parent function for exponentials is y equals a times b to the x. When our b value is greater than 1, we call it a growth function. All of the exponentials in this form go through the points 0a. In this case, we put a 0 in here. Anything to the 0 power is 1, so 0a, and then 1ab. So let's take a look at y equals 2 to the x. Notice it doesn't have an a value, or the a value is 1. So it's going to go through the points 0, 1, because our a value is 1, and then 1b, because 1 times 2, if we put that in, so 1, 2. When we graph it, 0, 1, 1, 2, all exponentials are curved. This one's growth, so it's growing from left to right. Now, as you draw the curve, do not let it cross the x-axis, because there is an asymptote there, which means that your graph can get really, really close to it, but it can never touch it. So as it gets lower and lower and lower, we're going to keep going, keep getting closer, but it's never going to cross over it, never going to touch it. The domain of an exponential is all real numbers, so we say negative infinity to infinity. Its range, though, because it can't cross this x-axis, is just 0 to infinity. The asymptote is y equals 0. Now we're going to take that parent function and we are going to do some translations with it. So since this now says plus 3, that is up 3. So we're going to take those same points that we had before, the 0, 1, and the 1, 2. And if we take 0, 1, and 1, 2, and we move them up 3, that's not going to change the x value, but it will change the y value. And it also changes the asymptote. So our asymptote of our parent function was y equals 0. If we move it up 3, now it's going to be y equals 3. So we'll put 0, 4, 1, 5, and draw in our asymptote. And we'll see that same curve, just everything has been moved up 3. So our domain is still negative infinity to infinity, but our range is now 3 to infinity, because everything moved up 3. All right, let's try some more transformations. On this next one, we have 2 transformations, both translations going on. This negative 3 means we're moving right 3, and then plus 2, we're going up 2. So we're going to take those same points that we had before. So from this parent function over here, 0, 1, and 1, 2. 0, 1, 1, 2. And we're going to move them to the right 3 and up 2. Our asymptote that was at y equals 0, if we move it to the right 3, since it's horizontal, it doesn't change anything, but moving it up 2 takes it to y equals 2. So when we do our graph, we dot in our asymptote, put in our points, and we draw our curve. Domain, negative infinity to infinity, range 2 to infinity. So those first 3 that we did are all examples of exponential growth. Now we're going to take a look at exponential decay. When your b value is between 0 and 1. It's called exponential decay, and our line will still be curved, but it will be decreasing. The good news is we still get to use those same rules as before, 0, 1, and 1b. So this time though, our b value is 1/2. So we have 0, 1, and 1, 1/2. You could see that our curved line is going the opposite direction. Our domain doesn't change. Our range is the same as it was for our original growth equation. And our asymptote is still the x-axis, which we say y equals 0. But what happens if we throw in a negative? That's going to transform our graph. A negative is a reflection over the x-axis. So our point 0, 1 is going to be 0, -1. And our point 1, 1/2 that we had before is going to be 1, -1/2. So 0, -1, 1, -1/2. We're taking that graph that we had before, reflecting it over the x-axis. Our domain, -infinity to infinity. Our range this time, -infinity to 0. But our asymptote didn't change. Still y equals 0. Now, when the negative is in front of the equation like that, we reflect over the x-axis. But what happens when our negative is in the exponent? So like on this one, y equals 1/2 to the negative x. Well, that negative up there is a reflection in the y-axis. So if we go back to our original points, 0, 1, we take the opposite of their x value, so that's not going to change anything. And then we have the point 1, 1/2. So now we have -1, 1/2. So 0, 1, and -1, 1/2. We're reflecting it over the y-axis, which makes a decay function look like a growth function. So -infinity to infinity, 0 to infinity, and y equals 0. All right, let's see how exponential functions look in word problems. The rate of inflation is 4% each year. I bought an Ultima in 2010 for $25,000. Write an exponential function to model this. All right, so an exponential function, remember, is always y equals a times b to the x. The a is your starting amount. So it started costing $25,000. And inflation means it's going up. So this is going to be growth. So with growth, we take 1 plus the rate. So our rate is 4%, which we have to change to a decimal. So 0.04. And then it's going to be to the x power. After you get it all set up, you do want to simplify what's inside the parentheses. So we're going to have 25,000 times 1.04 to the x. Part B, what would I expect to pay now for a similar car due to inflation? Well, if I bought that in 2010, and now it's 2019, my x value is going to be 9. So I have y equals 25,000 times 1.04 to the 9th. And then we can just throw that in the calculator. To the 9th. So that same car today would cost $35,582.80. All right, let's try another one of those. Again, another car example. When you buy a new car, it depreciates in value 8% each year. So if we take the same car that I bought in 2010 for $25,000, we want to write an exponential equation. So the starting amount is $25,000. This problem is talking about my specific car, what it's worth, and since it's depreciating, it's going down. So we're going to take 1 minus the rate, 1 minus 0.08 to the x. We will simplify that. So we have y equals 25,000 times 0.92. And so how much is my car going to be worth now? Again, we take the x value and substitute in a 9. So we have y equals 25,000 times 0.92 to the 9th. Throw that in the calculator. And even though I paid $25,000 in 2010, my car is only worth $11,804.03 today. Bummer. All right, so that's a little intro to exponential graphs and exponential equations, section 4.2.